much
start,
for
Predrag.
inviting
Oh, there you
me
go.
to
Good.
Newton Institute. About 20 years ago, we started on working on something that today is called exact recurrent structures, or what I prefer, richest term, recurrent flows. We were successful. It became clear that we're not making any progress by making these domains larger. And in our last collective meeting in Santa Barbara, I realized that we have to change the way we think about problem of turbulence in a rather radical way. And I'll try to explain it again today. The main idea is to give up evolution in time and think of problem of turbulence as a problem of enumerating admissible spatiotemporal patterns. When you look at turbulent or chaotic systems, the main idea of chaos, as opposed to kind of things you learn in physics courses. In physics courses, you basically, only thing you ever learn is harmonic oscillator, is Hooke's law. When you push on something, it resists and acts against it. And if it does it proportional to displacement that you cause by your push, that law is called Hooke's law, and result is oscillating solutions. Chaos and turbulence are very different. Instead of having a bottom of potential in which when you perturb a little bit, you run around the bottom, you have an inverted potential. So locally what happens is when you push, if you imagine that you push, the cat doesn't resist, it just runs away. Mathematically, the solutions are only the same. Instead of being sines and cosines, there's sinus and cosinus. I'll try to explain how this works. In three-dimensional world inhabited by plumbers, we visualize fluids as some three-dimensional volume, space this way, space that way, and there is a space another way, third dimension. But then there is also time. We observe a fluid. At every instant in time, we take a snapshot. Now, I cannot draw the snapshot because every point in the three-dimensional space has velocity associated with it, which is 3 dimensions. We take succession of such snapshots and we construct a video. Only computers can comprehend this video. Now, this is a conceptual talk, so I'm trying to explain how this is going to work if you are going to solve the problem of turbulence. So for purposes of this kind of talk, I will think a little bit more like electricians, for example, cardiologists that looks at the surface of the heart and sees a two-dimensional colored scheme, which is electrical activity or scan. We'll take a one-dimensional fluid. That one-dimensional fluid, and there'll be space this way. So we'll take succession of one-dimensional shots, and then each instant there'll be a velocity which is one-dimensional because space is one-dimensional. So in the way that a flame front changes its height is one-dimensional. So something that's orthogonal to the space. And we can consider this a scalar field, just a one number. We have captured space and time on three-dimensional plane, and the third dimension, the velocity field. Now, when you do experiments, what you see is that there are many correlations in that because we see shapes changing in time. But when you look at one of these systems in space-time, you see patterns. So we have mathematical language that says what patterns are allowed and what is the catalog of admissible patterns. Our task is to describe clouds. And at this point, Eberhard Hoff, 1948, comes in and says, the ultimate goal, however, must be a rational theory of statistical hydrodynamics, where properties of turbulent flow can be mathematically deduced from the fundamental equation of hydrodynamics. And this is what we will be doing. There are no statistical assumptions in anything we do. Everything follows from the equations of motion. Navier-Stokes, Euler, Kuramoto, Shivashinsky, you choose it. In the spirit of the moment, the sheep are Welsh. Why do we have sheep in a field? The visualization that comes from 19th century German mathematics, essentially, is to say that we have a field, so we have a piece of ground. I'll call it parquet floor because I'll tile it in a regular way. And on every piece of that field, there's a blade of grass. And one of these blades of grass, and that's the scalar field we're discussing. At position C, will have this value. To make further progress toward this field theory, we have to discretize things because computers cannot represent infinitely many values. So in this two-dimensional example, we'll start as our continuum spacetime, but we'll represent it every point by a pair of integers. This is still too big. So we'll take these integers to be modulo a finite domain, L in direction 1, L2 in direction 2, and the integer will just run from 0 to L2 minus 1. And because we want translational invariance, we'll make these domains periodic. So basically, we're replacing two-dimensional spacetime with integer valued tori. In this field, we used to have x divided every point, but now it gets replaced by a finite number of numbers, where each one of them is a function over reals. This is called scalar field theory. This latticized, so this is lattice scalar field theory. We are taking our space time. We think of it as a parquet floor. It's covered by regular tiles or parquets. We can account for each one of them just by specifying one point. We usually make it a unit lattice with unit spacing. And on each of these lattice side, there's a little blade of grass, and that is the state of the cat. You'll see why we call this a cat. This is actually a technical term. And thus we have turned our problem of enumerating, characterizing spatiotemporal patterns or shapes into a lattice field theory. This is a finite problem, but a high-dimensional problem. However, Hopf has something to say. What Hopf has to say is another level of madness. Hopf says the geometrical picture we are just constructing, the state space of possible states of fluid, is cool. However, it's not the most important problem of turbulence. Of greater importance is the determination of the probability distribution associated with the phase flow. So how does that work? I'll start by assuming we know nothing. Eberhard wants us to describe a probability. If you only had a lattice with one side, we would say, well, probability should look like something that's the most likely thing and unlikely things. So it should look something like that. It should have some width. Let's call it 1 over mu. It should have a mean. It must be a Gaussian. It's something that looks like mu square phi c minus the mean squared. Now suppose I take two sides. One side is in Atlanta, but the second side is on the moon. Then I can say the probability of my two-side system is a product of the two probabilities. Now, when we multiply two exponentials, the exponents add up. Now, if we assume that the same laws of physics apply here and in Saint-Jean, then that should be translation invariant. That is to say, we expect the mean to be the same in both locations. What we decide is origin of how we measure the strength of the field is arbitrary. So we can set the mean to be 0. And now we can write the probability of any number of sites as long as they're not correlated. First, let's define a lattice configuration, capital phi. Suppose we have some finite slab which is covered with lattice sites. And on each of these lattice sites, there is a little column, which is the value of the file at this lattice site. And that's what we mean by a given field configuration, means a bunch of real number, one real number for each site. If they don't know about each other, the probability, it's exponential. The thing in exponential we call action. So the action, an amazing function, it takes trillion numbers and returns one back. Returns a sum of squares of the field every place, because probability is multiplicative. So this sum is additive. There are infinitely many probabilities. So how are we going to compactly discuss them all? That problem has been solved in statistical mechanics. It's called partition function. And it says, I can take each probability which we have written in this exponential form. So for each configuration, we have the value of the action. Add a linear term dot another set of numbers. For each lattice site, there will be such a number, j, called a source, little j, at site z. We can take all these probabilities. We can integrate over all possible values for each site. So we write the humongous integral, one dimension of it for every lattice site. The result will only depend on the values of the source field. That's what's called partition function. What's good about it? Big J is a vector of J1, J2, Jn, which is the total number of lattice sites. When we take derivative of this thing, and then we set this J to 0, what will happen is this thing here is, remember, probability of all these guys being in the lattice configuration J. But this derivative took only one component down. When we set this to 0, this is now expectation value. If you take a second derivative, I have same probability distribution, and I look at the correlations of these guys. That's why people, in any situation where there are lots of little bits you have to keep track of, but there are some basic laws like translation invariance, homogeneity, isotropy, collect them all into partition function. It's a generating function for all probabilities and all expectation values of anything. So it's basically a total content of a theory that's described by probabilities. There is one problem with this theory. It's ultra local. When we constructed this, we started this know nothing. All of these guys know nothing about anybody. All these integrals are trivial Gaussian integral, and this has no content. It's a total bore. Now, the reason why I brought you to your attention anyhow is that next we'll introduce correlations. Ultra-local theory is boring. What do? We need some correlations. The simplest way to have a correlation is talking to my neighbors. How do we describe that? If we own a lattice, let's include the term I'm at Z and I'm talking only to the people if the distance on a lattice between these two sites is 1. So that's as local it can be. You know, wherever we are, That means that it's actually a function of the difference between the two, because that's a translational invariant combination. It's same every place. Then we would like it to be isotropic, meaning that I can set C to be 1 if I have any nearest neighbor, 0 if I'm not the next neighbor. Putting all this together, you get a plus operator. And I compare what I'm doing with all my neighbors. So sum over Z prime such that the distance is 1. For example, in one dimension, there's a minus here, plus here, minus here. If I'm on a two-dimensional lattice, I'll look at myself 4 times. So it's a very simple modification of our action. And now we have free field theory, a bunch of harmonic oscillators. This is bilinear in fields. When we put it in exponential, this is Gaussian in fields, so we know how to solve it. We go to Fourier modes, We've assumed translation invariance, what is called Klein-Gordon mass, is same everywhere. I can combine these terms and write them as a matrix on a diagonal. Now, and off diagonal, just in one dimension, just talks to its neighbors. 0 every place because we don't talk to anybody except closest neighbors. And when we get to the ends, we have to stick -1 here and -1 here. These are the boundary conditions, they're periodic. But this parameter, which I call mu square, if it's negative and I look at solution, I'll get oscillations. You'll have solutions which are oscillatory, like a mattress. But if it's positive, what particle physicists call Klein-Gordon mass, then only have exponentials, cinches and quotients. What you learn in school usually is this case, and what you have to learn in chaos and turbulence is this case, where everybody is unstable rather than stable. This is all very cool, but if you push something too hard, it actually doesn't always respond proportionally to your push. It might get stiffer, it might get softer. In other words, oscillators can be anharmonic. It's the most typical case. You sum up over everybody, add to it a quartic term with some strength. This is what kind of general scalar field theory looks like. Why am I subjecting you to this? I have to remind you about something that's very special to deterministic dynamics. All you need to know about determinism. This probability that we started with, in determinism, it has to be very narrow, because what we have in determinism, if you have an orbit that's connected by equations of motion, which I'll derive in a second, then there's only one solution for any particular state that's part of such orbit. So this probability will be so narrow, it'll have to be a delta function. It is intrinsic to determinism, it makes it different from quantum mechanics, and it makes it different from stochastic processes, for which the probabilities of necessity of some width. What does this mean for us? If we take this action and we vary it by any field on any lattice side, the variational principles of mechanics say I have to find solutions such that this first variation is 0. If you were doing this in quantum mechanics or statistical mechanics, you would say the most important parts are the stationary parts. In other subjects, this is an approximation. But for Lagrange and for Euler and for divinity that thought of all of this, this is the mechanics. You're only allowed to use these solutions when it deals with determinism. We'll call these solutions lattice states. So remember, we are computing probabilities of states. The probability of this state is such that I must satisfy Euler-Lagrange equations, and that is very sharp condition. It's a Dirac delta. And now this gives us a deterministic partition function. I actually know how to integrate over delta functions. Only contribution is where field is exactly where it is. And this is a function of the field. So you have to transform coordinates by Jacobian, and I get determinant of the Jacobian of this transformation. And that's it. Determinants of volume. So the state space is n-dimensional for scalar theory, but there are n possible lattice sites. And this is the volume, n-dimensional volume that describes the neighborhood of my deterministic solution. What's this thing? The first time I found it is in a paper by Hill from 1884. So I call it Hill's determinant. The Jacobian was a derivative of that function. That's what we call orbit Jacobian. And its interpretation, it's a Jacobian of what happens if I perturb every site on that lattice. Determinant of that thing, that's what we call Hill's determinant. Why do we care? Because that's the weight associated with particular classical solution phi c, which is now spatiotemporal solution. When you compute it, I'll just show you what it looks like. It's a banded matrix. On diagonal, I pick up the potential, evaluate on the diagonal, and then Laplacian, it just says, well, I have to see what's going on left and right. So there are two bands here. There's a periodic boundary condition. These determinants can be computed. Hill and Poincaré computed them. They have to do with translational invariance. So that means that discrete Fourier transforms will diagonalize them. We can compute thousands of solutions.
Got 5 minutes,
By those, I mean also Navier-Stokes and Kuramoto-Shivashinsky are field theories in this sense. And I'm sure you people in this audience can compute it for Navier-Stokes if you wanted to. Now you might say there is a way every orbit owns a fraction of the volume. So I'm partitioning space in neighborhoods. So if I randomly throw something in the state space, it'll land in one of these neighborhoods with the probability, which is given this guy here, this weight. It's a deterministic system, but it probabilistic interpretation comes through it in this way, that the state space is deterministically partitioned. Now, once you have this, you have things that we call cycle averaging formulas. I'll give you a very mangled sketch. Once you have this information, you would like to predict the friction on the walls of a pipe or dissipation. So I would like to have some observable, how much energy I burn in this particular part of the state space. You'll find some formula that says, the A is computed over the lattice. So I measure every lattice site. You can compute correlations. And now in the kindergarten version of the theory, you have probabilities that you will be in the neighborhood of a particular classical solution of your equations of motion. Measure my observable on each contributing solution, some configuration in space-time, and I will get the average of that quantity. I will be able to compute them once having computed the exact covariance solutions, a sufficiently large set of them. I'll be able to predict all observables, average over space-time, like some climate thing, like increasing mean temperature of the surface of the ocean. Now you don't believe me because you're working people and I'm just telling you something. So please give me a break. Go read Chaos book. If you don't have time to read, take the online course. You will discover, to paraphrase Bob Dylan, oh, you have gone to the finest schools, but nobody taught you this, and you need it. I'm done. Thank you.
Thank you very much, Predrag.
20 years ago.
Okay, we do actually have time for a couple of questions if people.
No, I was at 24 minutes and 46 seconds. So
yeah, indeed, fantastic job. Okay,
I worked at least 4 hours to make it that time.
I'm sure you did. Here's Martin Overlock.
Yes, thank you for the talk. Maybe I have just a quick comment. I mean, you're citing Hopf various times, and we do know that Hopf has this famous Hopf functional equation derived from Navier-Stokes. So can you comment on how you solved that one? Because that is one of the key questions in turbulence, how to solve Hopf functional equation.
Well, if you're thinking of the same equation as also Lev Davidovich Landa worked on, at that time, there was very little they could do because they did not have machine learning, supercomputing, etc. So this is basically saying if I have a bunch of oscillators, it'll look turbulent. I think, I might be wrong, but I think this is not our problem any longer. So maybe that's not a good answer, but that's my answer.
Other questions?
Yeah.
Other questions for Predrag? I don't see our next speaker online yet, so we have a minute.
Predrag, I would have a question. In your model, can you compute the spatiotemporal solutions analytically then? Is that the main difference to the turbulent flow, or?
We are writing a bunch of papers which are basically like Bernoulli maps and like cat maps. So these are things you can work out analytically, and we are doing them for pedagogical reasons. So you can see how these computations worked and how you use symmetries to speed them up, and the computations are possible. Now, when you go to fluids, we've only done Kuramoto, Shivashinsky. Matt Goodorf has done amazing work on it. We can find, as many solutions of Kuramoto, Shivashinsky on spatiotemporal patterns, spatial temporally periodic, no analytic anything, of course, but the theory is put together in some systematic way.
So you have a systematic way to compute the solutions for the Kuramoto Shivashinsky, if I understand, or you're still relying on some guesses?
This is really engineering. You're solving optimization problems. So basically, you make a guess for the solution in which you understand, I have to have 3 vortices here and 2 streaks there qualitatively. And then you run it through your optimizer. What the optimizer does is it makes sure that locally, the tangent space satisfies the partial differential equations. So you take a global thing, you optimize it locally, you can do it extremely well. And, the basic idea is that there's some basic building blocks. In Kuramoto Shivashinsky's, you have rolls, you have some wiggles, you have, splitting or destruction of rolls. So they're basically 3 patterns. You can glue them together to produce bigger patterns, and you can build them. So that's what we have done in the practice. Now, you people can do this for Navier-Stokes. John Gibson is an adult now, and he has to do all kinds of horrifying things that professors do, like run departments, etc. So we cannot wait for him to do it, but you can do it. So speaking to, this might seem to you absolutely, from the moon, but this is what we have to do to understand spatiotemporal phenomena. We have to put space and time on equal footing. In particle physics, we are very used to this because, Minkowski space, etc. That's all how field theory works. But it turns out you actually need it also. It's essentially Newtonian physics, that time has different equations than space when you look at partial differential equation. But it's absolutely essential to treat them on equal footing. And I should say that when you do these global problems, when you do things forward in time, to be able to compute some coherent structures, you have to be amazingly precise. Machine level precise. And that's why we were defeated on increasing our domains. You know, Mark and others, we have computed very successfully exact coherent structures on small domains, but could never do them on bigger ones. Now, in these problems, when you do global optimizations, there is no exponential instability of anything because there's no time evolution or space evolution or anything. And it's good enough if you compute it to 3% because we're doing fluid dynamics. We are not doing celestial mechanics. These guys, you can produce very large patterns correctly.
Our question here, and we don't have our next speaker yet, so we're going to let you keep going. Here's Alexander Morislav.
Thank you. Hi, Predrag. Just a technical one. I mean, what you're doing is not dissimilar to Dominici-Janssen, if you wish. There, we know that the determinant can be absorbed into the functional measure, and you don't particularly care when you're doing RG, for instance. Why do you care about the determinant?
In this case, it just turns out that this determinant is the volume of the neighborhood of your spatiotemporal solution in any finite number of dimensions. You know, we did it one space one time, but you should do it in 3 space or 2 space one time, depending what kind of fluid dynamics you're doing. And we care because they turn out to be the volume of the neighborhood. So they're totally central and crucial. And I guess, you know, this is really the new, in this talk, you know, I've tried to give you a different, in Kjell's book, we derived it forward in time. In this talk, I tried to explain how you work in space-time, where you have space and time on democratic level. For one-dimensional evolution in time, you get the same answer. So this determinant I gave you is the determinant that people who study coherent structures already know. We compute it forward in time as it's called, you know, Jacobian of the flow of 1 minus Jacobian determinant is the usual way that everybody knows. Now, in this more democratic way of space-time, you actually compute Hill determinant. And that's the real content of the theory, you know, how important every solution is. This answers, you know, the reason why I gave this talk is because of yesterday, where Johan, as always, was skeptical. Yeah, he might be right. And for kind of problems that Johan does, this doesn't help very much. But for kind of problems where you have kind of uniform turbulence every place, and you see same kind of patterns like you see in the skies, this should be good. You know, it has to be tried, as Tobias said yesterday.
So inspiring talk. Do you think you can derive K41 from your theory, or it could be potentially consistent with K41? I
don't know. You know, this has been inspired. All of this is inspired by transition turbulence. You know, so this is all inspired by work where you don't have many scales, because basically a transitional turbulence, you have geometric scale and you have some rolls and wiggles, which are, you know, not much smaller than geometric scale. So there's definitely no going to Kolmogorov kind of scales. So I have no idea. You know, the idea is in Eulerian setting is that maybe you can rescale yourself. There could be some renormalization theory of solutions that get you to larger scale. You know, how this would work in now, you know, we saw previous talk, we saw beautiful things of volcanoes. And now what's amazing when you look at any of these pictures, you know, Reynolds number might be 10 to 27, I don't care, but I recognize this picture. Why do I recognize this picture? Because you look at it and you see the shapes. You see the shapes, you know, the whole cloud above the exploding volcano is constructed of little patterns that satisfy the Stokes equation or appropriate equations of things. So, you know, ambition here is to describe them, the building blocks. So even for very Reynolds number, I think that part might work.
Let's thank Predrag one more time for fascinating, thought-provoking talk. Thanks, Predrag. So we don't have our last speaker for the afternoon, so I think we'll just go ahead and start I think we have coffee now. And hopefully coffee. And then the discussion is that at 4? The discussion starts at 4 o'clock. Thanks, everyone.